Hi blog. So welcome to this small video. Thank you very much to Ms. Julie Beltman and to Mr. Chris Vernon who invited me to have this little space to share some of the current work that I am doing to graduate from my PhD in math. Uh, so the idea is the following. The excuse is to discuss this question. Does personal experience play any role in the formation of claims in mathematics? And I believe that this question can be answered in the sense of theoretical math in many interesting ways. One of the ways that I think that we should explore is by hearing the story of this guy. So his name is Srinivasa Ramanujan. He was an Indian mathematician who came up with formulas like this. So it is a very cool way of understanding pi. So if you ever asked Ramanujan, where does this formula came from? Like, how did you find out this formula? He said, like, it came to me in a dream. It is very interesting because, like, he had very like non-formal education in mathematics when he came up with these formulas and with a lot of his contributions to analytic number theory. He wrote some letters to famous mathematicians that worked at universities, and most of them ignored him except for this guy, G.H. Hardy. So he read the letters that Ramanujan was writing and he said, like, he's right. So it is very interesting, like, where the claims in mathematics come from. Like, can they come from a personal experience such as a dream? And the answer is yes. Of course, even though that they come from a dream, they do need to have a very rigorous proof and an argument that the mathematical community need to accept. I strongly suggest you to go watch the video, The Indian Genius Nobody Understands. It is a very tragic story that will help you reflect around colonialism, about what is truth in mathematics. I just think that it's very, very cool, and it's a suggestion. Okay, so, but that is not what I am here to talk about. I am here to talk about, to answer this question, or to at least think about it from the perspective of applied maths. In the light of my research. So in the handout that you should already have seen, you have like these three models. And in these three models, like, I am portraying like three different situations with three different models. So the first image comes from a research paper of 2003, where they study the Scottish Gaelic in Sutherland and how it declines. The second image portrays a study of Catalan in Catalonia. And the third one is the one that we are proposing, and it is about Maya in Campeche. So the three models come from three different perspectives, three different philosophies of how to understand language competition. And so, just like very briefly, I want to say that in Mexico, as you may already know, we have 365 different indigenous languages. And from those 365 indigenous languages, some of them are going extinct. This is a graph that I made from data in INEGI. So you can see how indigenous language speakers have declined in the last 100 years. So if you ask yourself what is happening in 1930, you will see that 16% of people were indigenous language speakers, and today only 6%, around 6%. So there have been a huge decline in indigenous language speakers, but this decline has been decelerating. Like, you can understand this linearly. If you look at the slopes, you will see that the slopes are continuously decreasing. This suggests a nonlinear model to to understand how indigenous language speakers change. UNESCO established this decade to be the decade of indigenous languages in the world because there is a lot of evidence suggesting that there is a big decline in the world of indigenous language speakers. So, this mathematical model comes from 2003. This is a model, the first attempt to model language usage using differential equations comes from Abrams and Strogatz. So, what Abrams and Strogatz suggests to understand or to simplify so that we can use an equation to model how the populations change. So he assumes that they assume that the population is divided into two parts. So the speakers of X and the speakers of Y. So you are either an X speaker or a Y speaker. In this model, we have no bilinguals. So how did they apply it in the real world? What they did is so for example, if you are a bilingual of language X, I'm gonna consider you as a part of the population X. So in their applications of real world scenarios, they assumed that everybody who was a bilingual was a part of population X. So this is a model of language understanding, no? So everybody who's in X is a person who understands an X language, and everybody who's in Y is a person who does not understand X language, so only understands Y language. X and Y are fractions that add up to 1, no, are the proportions, the ratio of speakers of X and Y. And so how this model works is that it is a differential equation in which basically we describe the following. So the change of X in time, of population X in time, it's gonna change in the following way. It either have members of population Y coming in or members of population X coming out. So how many members of Y are going to go into X? Well, you need to know the probability of turning into an X member if you're in Y, and multiply that probability by the amount of speakers in Y. In the same way, how many members of X are going to leave population X? Well, that is, if you know the probability of being in X and turning into Y, and multiply it by the amount of members in X. And now the hard part is, how do we describe these transition functions? How do we describe those probability functions? And the idea that they propose is to say okay, so the probability to go from Y to X is going to be proportional to a certain number that we're going to call the attracting population. So the idea of putting an exponent over the size of the population comes from kinetic gas theory. The term volatility comes from a gas theory, in chemistry. So here we are saying the probability of becoming an X member if you're in Y is gonna be proportional to the amount of speakers in X that are part of the attracting population. So it is not that every member in X attracts you to become an X member, so it's just a fraction that is called the attracting population that depends on a certain volatility parameter. This is the force, the attracting force that population X exercises over population Y. There is another number, a constant, that we will call a prestige parameter, that it's a number in between 0 and 1, being 1 extremely prestigious and 0 non-prestigious at all. And then to describe the other transition function, we do, and this is very important, a symmetric idea. No, so the attraction force that population X is gonna suffer from population Y is gonna be the same A, and the prestige is the complement, and also like if this is S, this is 1 minus S. So like there is a symmetry in between these two populations. No, the attracting force that X experiments from Y is the same as the attracting force that Y experiments from X, and the prestiges are like complementary. With this, we can come up with an equation, and it is a gorgeous equation that one can study and understand, and it's beautiful. And so what happens with this equation? Like, this is the big idea. If you were not paying attention, you were falling asleep, you just like forwarded up to here, like this is an important moment. This model suggests that every language is gonna die. Oh, if I have this scenario, both languages, one of them needs to die and the other one will survive. Like, it doesn't matter what are the initial conditions, both languages will die. And so these researchers applied this model to languages that were very clearly dying. Like, one of this is from a Scottish Gaelic in Sutherland, the other one is from a certain particular place in Quechua, and some other two tongues that I don't even remember, but like I could put them in the description of the video. I'm gonna link the article. So this language can be applied, this model can be applied to scenarios where languages are clearly dying, and it does work to represent some scenarios. But you may know that in populations, or you may have noticed that in real life, not all languages are dying. Some languages are surviving, and maybe that, and maybe the fact that some languages are surviving depends heavily on the existence of bilinguals. So, like, having bilingual populations may be the reason why languages do survive. And so that is what Mira and Paredes, two Spanish researchers, propose in a certain model. They say, like, okay, so if instead of thinking of just two populations, we actually include a third population, so like we have X speakers, the monolinguals of X, Y speakers, the monolinguals of Y, and B, a bilingual population, and we, of course, I cannot go from X to Y without being first a bilingual. No, I cannot wake up one day, I go to sleep being a monolingual of Spanish, and I woke up the next day being a monolingual of English. Now, like, there is a transition in between the two languages. If I want to go from X to Y, and now this transition functions work the same, but now I have another parameter that it's called like an interlinguistic parameter that measures how similar the two languages are. Now I do not have only one equation, I need two equations, and so my stability diagram needs two dimensions. And so if you were not paying attention, what I want to say, important right now, is in this model, when I include a bilingual population, it is possible that I have a stable equilibrium point between the three populations. So it is possible that these three populations coexist in a long term. And this model has also been applied, and the two applications have been like very famous and interesting. The first one was made by Mira and Paredes, and the second one was made by Seoane, both of them in the context of Spain. In the first one, they are studying how Galician is changing in the region of Galicia, and in the second one, they are studying how Catalan is changing in the region of Catalonia. And so what I want to point out that it's very interesting, even the colors are the same. So red are the monolingual speakers of Galician and Catalan, and as you can see, like, both languages as monolinguals are declining. Like, both models predict that Catalan as monolingual will disappear eventually. And thanks to the bilingual populations in green, it is because that both languages will survive, and that is very interesting. Also, I want to point out that the proportions in these graphs are huge. Here, we're saying that almost half of the speakers in Galicia are speak Galician, and here I am saying that almost 80% of the populations in Catalonia speak Catalan. So like the proportion of speakers are huge. What happens in Mexico? When I try to apply these models in Mexico, look at the proportion of language speakers, of indigenous language speakers in Mexico. So here I have the state of Guerrero and Nahuatl. Like the amount of monolingual speakers or bilingual speakers is like super tiny. So what is happening? If I apply in both models, when applied to the Mexican scenario, both models suggest that all indigenous languages die. This brings a lot of ethical implications, a lot of this is where we start asking questions, no? Like, so if I cannot apply a model or when I am applying models to describe the scenario and all the models are saying that all languages are gonna die, then I need to start asking, like, is it true that all languages are gonna die? Or is it a problem with the model? Here I have a couple of graphs of two scenarios here in Mexico, Nahuatl in San Luis Potosí and Otomí in Querétaro. And so like the differences are very subtle, no? Like how do I determine like this set of points, the Nahuatl speakers and the Otomí speakers, like how do I determine that one is gonna die and the other one is gonna survive? How do I study it if the current models are not like giving me enough, are not depicting reality accurately? So that is where my proposal comes, no? Because I am not accepting that all languages are dying, all Mexican languages are dying. That is my like personal belief that I am putting into the equation and what motivates me into making a change. In the same way as maybe the researchers, the Spanish researchers were like, I'm gonna twist the model, I'm gonna extend it because I don't believe that all languages are gonna die. In the same sense, that is like my thought. My thought is like, I am not believing that all in Mexican indigenous languages are gonna die, so I need to extend the model. I need to make it more complete in a sense that I can depict like indigenous language speakers Mexican reality. So what am I doing? It's like a very easy and simple extension. I am going to the Abrams and Strogatz model. I am assuming that my population, because like in the bilingual and monolingual speakers are like two very small populations. I am adding them together. So this is a two-phase system. I am assuming in the same sense X are the speakers of like are the monolinguals and bilinguals of a certain indigenous languages, and Y are the speakers of like a dominant language. And what I am changing are the forces of attraction. So I am just saying it is easier for a speaker of an indigenous language to go to Spanish than for a Spanish speaker to go into an indigenous language. That is the assumption that I am doing. I am assuming that there is no symmetry in those two forces, or that those two forces are different. That is the only extension that I am doing. And when I apply that extension, now I have more scenarios. Now coexistence is possible, and of course, like this is a stability diagram. So like if you remember that graph in which there was only one scenario, the dying scenario, now I have more possibilities by making that assumption, by making that extension. I went and I took like the most spoken languages in some states, the majority in the south of Mexico. And well, what happened is that I actually concluded that there are some languages that are in an extreme high risk of disappearing. That is the Nahuatl in Hidalgo, Otomí in Hidalgo, Otomí in Puebla, and Otomí in Querétaro. While we have like languages that have like a stronger survival probability, no, that is like, for example, Mazateco in Oaxaca, Maya in Campeche, Maya in Yucatan, Maya in Quintana Roo. So like, well, I made this small video just to show that sometimes research in mathematics can be driven by beliefs, and this should also make us ask the question, so what do we do when mathematics is not depicting the reality that we see? And it's an opportunity for sharing the research that I am currently doing. Thank you again, Julie and Chris.